Hello, you all. I welcome you all to my channel. I'm back here. I know I have missed a lot of content and videos, but now I have completed my exams and I shall be resuming our studies. Today, I'm going to discuss a rudimentary topic of our curriculum, acid base analysis. So, why do you think we have to learn acid base? So the enzymes, the muscles, the nerves, and for oxygenation and metabolic functions, we have very narrow therapeutic pH. So now this pH is of range say 7.36 to 7.44. So any change in this system can be a problematic to us. So that's why we have to maintain this pH. And as we all know, pH is nothing but it is minus log, that is, it is inversely proportional to that of the H plus value. So minus log of H plus. So as the pH is decreasing, the curve shifts to the right. That means the acidosis is causing the shift to the right. Increase in 2,3-bisphosphoglycerate shifts to the right. The curves is shifting to the right. Decrease in oxygen level will shift the curve to the right, and increase in the carbon dioxide level will also shift the curve to the right. So this is the uh, we have been studying this curve, okay. And so now we have total 7 crore of H plus which are secreted in our body. That is an approximate value, and which is cellular toxic. Now if it reacts with the cell and the cell compound, our body but our body has this acid base system. So if it reacts, then all of the cells are gonna destroyed, right? So this is cellular toxic. So that's why we have to have a acid base buffer system in our body. So we have the three buffering system. There is a chemical, there is a respiratory, and a renal buffering system. So chemical buffering system provides us with an immediate response. Respiratory buffering has a fast response, but when it comes to the renal buffering, it has a slow response. So as we are aware, there is a acid that is an H plus, and there is a base which is actually causing Ha, right? So there is this H plus, and this is the bicarb, and this is the H2CO3 which is being created. So this is a conjugate base, right? Now, when it comes to a pKa value, which is nothing but pH at which the acid will be 50% in a A minus state and 50% in a HA state. So that is the pKa value. So pH is equal to pKa plus log A minus upon the HA. Okay. So if the pKa say is less than 3, that means there is a strong acid, right? So it will exist in HA form more, and we do not want that. We want A minus form more, so that the A minus then combines with that of the H plus, so that there is an HA formation is there, right? So weak acid is actually an excellent buffer. Remember that. So we need a pH say like 6.1 or so. So bicarb can be a extremely good for our system. So H plus with the bicarb. So that is the H2CO3 formation is there, and this will act as a buffer. And when it splits, there is an H2O and the CO2 which is released. We are all aware of that, right? And no, so there will be a CO2 which will be exhaled out. And when there is decrease in the PaCO2 value, there would be a respiratory alkalosis, which is a compensatory respiratory alkalosis. I hope you have all got the idea how there is a metabolic acidosis as the bicarb is being used up. Okay, so the bicarb is being used up, so that why there would be acidosis in this. Okay, because there is no bicarb. And when there is a decrease in the PaCO2 because it is being exhaled out, so there would be a respiratory alkalosis. Okay, so when it comes to a chemical buffering system, say we have a bicarb, which is excellent extracellular buffer. This is MCQ, okay. Then we have a second system, that is a phosphate buffer system, that is the H plus will bind with the phosphate buffer, so that there is this effective intracellular buffer formation is there with the pK value of say 6.8. We have remember that pK value should be like 6.1 for the bicarb. Now when the hemoglobin combines with the RBC, so there is also a buffer system which is being created, which is say of 7.3 or so value. So how can I get metabolic acidosis? Now acid is added to the system, and that could be because of ketoacidosis, same endogenously, or it could be an exogenous, that can be a methanol like compound. So now bicarb combines to form a buffer. Okay, so it is being used up. Now there is no bicarb in the system, so what will happen? There will be acidosis, so that is metabolic acidosis is there. Now whenever this is the second phenomenon, how I will get a acidosis. So the first was the endogenous or exogenous acid is given to the body. The second thing is bicarb is being lost. Okay, so it could be actually through the GI loss of the bicarb, or it could be a renal loss, we don't know. Okay, so there are two phenomena through which I can get an acidosis picture. So now let's see what is an anion gap. This is very crucial in the ICU people and people staying in intensive care, or people who are not aware of the cause of the nausea, vomiting, dehydration. So this is very important in anion gap. Okay, so which is nothing but it is the measured and unmeasured cation. Okay, which is actually equal to measured and unmeasured anions, right? So we calculate the measured cations minus the measured anions, which is actually the nothing but it is the anion gap. So anion gap can be written as unmeasured anions minus the unmeasured cations. Okay, so this is the formula which we have created. The measured and the unmeasured cations is equal to the measured and unmeasured anions. So when we are just having the anion gap, it is nothing but it is an unmeasured anions minus the unmeasured cations, which is nothing but sodium minus the chloride plus the bicarb. Okay, so remember this formula. Okay, which is very different from the urine anion gap, which we'll be studying later part, but remember this formula. Then now when there is a bicarb which is being lost, so which is nothing but it is an anion, right? The negative ion. Okay, so always there will be a compensatory compensation which will be provided by the chloride. Okay, chlorine. So the anion gap remains the same. Okay, so it could be a normal anion gap metabolic acidosis, or say there will be a chloride which will be increased, and that could be a hyperchloremic metabolic acidosis. Okay, so now there could be another thing, that is the bicarb is being lost. So there is this is used up for the buffer system. We have already seen that bicarb is being used up, and there will be acidosis, remember. But as there is unmeasured anions will be also increased in this. That means there is this formula, right? So bicarb has been used up. Okay, so now what will happen? There is lesser degree of this value. Okay, so now what will happen? The unmeasured anions, okay, this unmeasured anions will be increased, and that will cause increase in the anion gap. So there are two things, a normal anion gap, or we have the high anion gap, so hagma or nagma. So now, what is the metabolic acidosis causing? There could be an acid which is generated, or there could be alkali loss. So now, if the acid is generated, that is a ketoacidosis picture. So it could be because of alcohol, starvation, and diabetes, which we are all dealing with. The second thing could be a uremia, a salicylate poisoning, methanol, ethylene glycol, and lactic acidosis. Okay, so these are also causing acid which is generated, and this will be causing a high anion gap metabolic acidosis. When the alkali is being lost, okay, so bicarb is lost, and there will be increase in the chloride, that is a compensatory increase. So that will be a normal anion gap metabolic acidosis. Now, the first thing we have already discussed, there could be GI loss, or there could be renal loss. If there is a renal loss, remember renal tubular acidosis, and if there is GI loss, we can have VI POMA or ureterosigmoidostomy. Okay, so this much is very important. Remember these two things, acid generated and alkali loss. Okay, so now let's jump into the renal buffering system. Okay, so renal buffering system is something which is a slow one. Now there will be a volatile acid which is excreted through the kidney, and there could be a non-volatile acid that is actually 1 milliequivalent per kg per day, which is equal to 80 milliequivalents. Okay, that could be a sulfuric acid, phosphoric acid, and so on. So excreted through the kidneys. Now we need to excrete them out. How do we do that? So the if we see, there would be a at the level of the PCT, there is a sodium and the H plus exchanger that is seen. Along with that, there could be a sodium and the glucose also co-transporter, which is seen. Sodium and phosphate co-transporter, and sodium and amino acid co-transporter. So this is very important picture. There are 4 transporters across the PCT. Now what will happen? as there is this filtered bicarb whichever it is coming. So because of the carbonic anhydrase enzyme, so H2CO3 is being created and H2 and CO2 has been split. Then we have this has been taken into the PCT, and then we have the H2CO3 again formed with the help of the carbonic anhydrase. Again it is converted H plus and HCO3, and HCO3 is being excreted out. So this is the whole picture where we can have the HCO3 being excreted out through the PCT. So of course, there is a renal tubular acidosis if there is a PCT which is involved. That is a type 2 renal tubular acidosis we see. So that is a proximal tubule defect. So there would be a sodium bicarb exchanger defect or a carbonic anhydrase defect. This is a genetic defect that can be seen, which can be associated with cystinosis, Lowe's, Wilson's. Okay, there could be such diseases which can be galactosomia, tyrosinemia. They can be associated with it. Now, RTA type 2 in adults can be because of the myeloma, because of the tenofovir, cyclophosphamide, tetracycline, gentamicin. It could also be because of hyperphosphatemia, or it could be also because of the post-transplant patients. Okay, so remember that also. Now, so this is causing a normal NAND metabolic acidosis. Okay, so this is something which is causing PCT if it is not working. So the salt and water wasting is there. Now, there would be a defective arterial volume, and of course the RAS will be activation will be there, aldosterone is released, and thus there will be hypokalemia. So all the symptoms related to hypokalemia, including that of the twitching or weakness or paralysis, all that stuff. Okay, the next thing that could be seen is because we have sodium and phosphate transporter across the PCT, so there will be bone mineral changes also, rickets like changes. Okay, and then there could be sodium and glucose transporter also, so that will be glycosuria which will be seen. So this is very important. That's why that diagram is important, because there are 4 transporters that are there. Again, when it comes to that of the collecting tubule, at the level of the collecting tubule, we have something which is H plus and ATPase pump, and there is a H plus K plus ATPase pump also. So whatever the now ammonia is there. Okay, so now there is this ammonia and the phosphate buffer. So ammonium ion will be formed, H plus with HPO4, that is will be formed, H2PO2 PO4 will be formed. So this is the working where the bicarb and where the ammonia and the phosphate buffer is being acting at the level of the collecting tubule. So when it comes to that of the H plus ATPase defect, or say H plus K plus defect, that is a type 1 RTA, distal RTA. The most important thing is the Sjogren's you have to first of all rule out, and again other autoimmune things like hyper gamma hyperglobinemia, or we have the pictures like that of post transplant patients. Okay, you have to think of that familial hypercalcemia, you have to think all these things. So but the most important thing is the Sjogren's, which is very important. So here now what happens is there will be a calcium which is not absorbed from the bone, and that will be causing a rickets like condition, and there will be severe normal. So urine sodium plus the urine potassium minus the urine chloride. Okay, so this in the result RTA, H plus K plus ATPase or H plus ATPase is not working. H plus which will be not formed, so H plus will not be available to bind with that of the ammonia, and there would be no H plus and NH4 plus which will be there, and unmeasured cation will not be there. So urine anion gap will be of course high. So and urine anion gap is slightly negative in case of the GI loss. So in the distal RTA there would be a urine anion gap which will be high, and in case of the in case of the GI loss that will be slightly negative. So this is how we can differentiate between that of the between the distal RTA and that of the GI loss. So hope you have all found this video to be useful. Thank you so much for watching.